And so in the last session, we discussed the poor correlation between the convective parameters that are being used in forecasts. And the fact that the forecast models are wrong primarily because they're not taking into account the electrical energy. So what you see in this graph on the left is the typical convective information used in forecasting. In this case, it's storm relative helicity and CAPE, convective available potential energy. The graphics are similar, whatever parameters you wish to use. And as you can see, it's impossible to forecast using this data. If this data was useful in forecasting, then all the data points would fall along either the red line or the blue line. But as you can see, there are some close data points, but nothing actually falls on the data line. So the forecasts are inaccurate using this data. But if we use the data on the right-hand side, the two graphs, one on the left using cloud to ground data is a poor correlation, but it's still more useful than the data on the convective information. But the far right graph represents total flash counts of lightning with vertical integrated liquid. And as you can see, there's a very strong correlation, a very good relationship that can be used to predict storm intensity in forecasting. So the current forecast models by the SPC, when they say this is the convective outlook, those models are very poor. The skills are very low. So Brian and I were talking about a moderate risk event one day, and Brian says, well, all the ingredients are present. Remember that conversation, Brian?
I do.
And so all the ingredients that meteorologists used were present, but not all the ingredients that affect storm production were available. So what do you think we need to add to make those forecasts more accurate?
Beyond my modeling capability, if you could figure out how to integrate that.
I don't do forecasting, but fortunately there are people who do. And so there's a...
Well, that's more like modeling. That's modeling change there. If you're going to change the algorithm to be able to incorporate different science, I mean...
different parameters.
Yeah.
And so that's been done. You see this paper by Stephen Goodman, adding electrical activity to the forecast will improve short-term weather forecasting. And so these models have been developed by the National Center for Atmospheric Research, and they're getting good results. And we'll look at that a little more.
Yeah, that's I'm talking about the title there, and AMPERE stands for Active Magnetosphere and Polar Electrodynamics Response Experiment. When it changed from a NASA Explorer proposal to something to NSF, I was actually flipping through the E's in the dictionary, looking for another E because Explorer had to be replaced by some other E word. Let's talk about fundamental quantities. This is my box model of the magnetosphere and the ionosphere that helps me organize some of these things. First of all, there's flows, which is related to electric fields in the magnetosphere that way, and it's related to convection in the ionosphere that way. And those two are linked by the field lines, which are nominally equipotentials, unless you're an Aurora fan, like Bill Lutko is an Aurora fan, and then you object, and you say, wait a minute, that isn't always true. But for the purposes of my box model, it's true. And then the next moment in the Vlasov equations is momentum. And these are the momentum equations which are related to perpendicular currents. And if you integrate those along a field line, you get field and line currents. And those are the things that then flow to the ionosphere. And those are related to the perpendicular currents in the ionosphere, which are familiar friends, the Hall and Pedersen conductances. And it's the divergence of those that's related to that. And the nice thing about that is that those currents have to be conserved between low and high altitudes if you're below the time regimes where you care about that. And these currents are conveying the stresses. So these are conveying potential and flows. This is conveying stresses, which is related to momentum. And if you want to talk about energy, the magnetosphere at high altitudes is the dynamo for the system. Let's set neutral winds aside for the moment. And primarily the ionosphere and thermosphere is the drag on that, and the dominant energy flow is electromagnetic energy flow, which you can measure with the Poynting flux. So now let's look at some of the quantities we have here and see which ones are the fundamental ones that we would have access to measure. And the electric fields are one of them. And that's why people were going after chains of radars and the super darn high latitude radars, because if you get the electric field, you can begin to diagnose some things about that. You can begin to get pieces of the momentum, and you get part of the dissipation part of the system and the energetics of the system. So if you get the electric fields, you're making a lot of progress there. If you can measure magnetic fields and derive field line currents, you notice that you get this part, and you can actually diagnose what's happening at the high altitudes and relate that to the distributions of plasma, at least through these uncertainties, and you can close on the energetics of that. So those are two of the key parameters that you want to try to measure to try to close that system. So formally, this helps set the stage in that sense. So this is the idea. If you have a satellite at low altitude flying through this kind of a system, it will see the magnetic perturbations created by these currents. And it will see primarily between these two sets of currents right in there. That's where the biggest perturbations will be. So if you have low Earth orbiting satellites passing through the currents, they will detect them. You can use those currents, and then ionospheric currents actually shield that so that you cannot diagnose these field line currents from the ground. What you see from the ground are the perturbations related to the Hall currents. And that's removed from the field line currents that I showed in the previous slide by two different layers of the conductivities. And so it's a little bit harder to do that. That's how people were first, as in people, as in that people. Art and Kimide and others first used ground magnetic perturbations through the conductivities to try to derive some of these things, which is where the AMI procedure derives from. And you can see this is all converging on that bill. The primary discrete precipitation, which is the downgoing electrons, which create the brightest aurora, are co-located with upward currents. So they will be located in the upward region 2 currents in the morning and the downward region 1 currents in the evening. So the oval is actually shifted a little bit towards the morning relative to the field line current and the convection distribution.